So the topic for this next couple lectures is a statistical test known as analysis of variance, or an ANOVA. And we're going to first begin our discussion of ANOVAs by looking at the limitations of another test that we've gone over, which is a t-test. And we've shown it to be very good and effective at being able to establish the statistical significance between two different means. But suppose, for example, you weren't just comparing two means, but you were comparing 3 or 4 or more means. Can you just do multiple t-tests for each one of those? You can, but it's not actually statistically correct or appropriate. And the answer as to why that is because your odds of committing a type 1 error increase. Remember, type 1 error is rejecting the null hypothesis when it's actually true. And we denoted the threshold value for the probability of making a type 1 error as alpha, which in general is 0.05. So if the null hypothesis is true, the probability of not obtaining a significant result is 0.95, or 1 minus 0.05. Now, if you do 2 tests on the same set of data, the probability of not obtaining a significant result in each one is 0.95 times 0.95. It's the probability of 2 independent events. It's just the product of each one. And so that becomes 0.9025. So the probability of making at least one type 1 error is 1 minus that. So 1 minus 0.9025, which is now 0.9075, close to 0.1. So now our odds of type 1 error have increased from 0.05 to almost 0.1. So we can't keep the significance fixed when we start doing multiple tests. Now imagine that you were comparing 4 different groups in the same set of data. You'd need to do 6 different t-tests to test for significance. And if our 4 groups are A through D, A to B, A to C, A to D, B to C, B to D, and C to D. So the probability of not obtaining a significant result is, if it were 0.95 squared for 2 tests, it's 0.95 raised to the 6th for 6 tests, which is now 0.735. So the probability of making at least one type 1 error is now 1 minus that, which is 0.265, not 0.05. So basically, your odds of rejecting the null hypothesis when it's true increase by a great deal when you start doing multiple t-tests on the same set of data. So we need another way to be able to analyze our data set while keeping our significance level, or our alpha, fixed. So one way we can do that is to use a lower alpha to be more conservative. Instead of 0.05, we can use a lower one to be more conservative. And one way to do that is through what's called a Bonferroni correction, where, say, you run n tests on the same set of data, you adjust the significance for each test to alpha divided by n. So using that example earlier, we were running 6 different tests. We would set the significance for each test at alpha, which was 0.05, divided by n, which was 6. So the disadvantage of this is that it can lead to many false negatives, especially if you're running hundreds of t-tests on the same set of data, because your alpha rate just drops to next to nothing. So another way of doing it is what's called an analysis of variance, or an ANOVA. And so the major advantage of an ANOVA for doing multiple comparisons is that it keeps the alpha at 0.05 the same across all comparisons. So you don't have to worry about doing corrections at all. So let's learn how to use an ANOVA and what everything means through by just doing a slow step-by-step example. And so we'll assume the following data set, which looks at the time to complete a puzzle in minutes following 3 different drug treatments. Okay, so you have treatment 1, treatment 2, and treatment 3. And the n in each case is 3, so there were 3 different measurements made for each treatment. Okay? So an ANOVA answers the following question basically. It's how much of the total variation in the data set is due to variation within each group versus variation between each group? If most of the variation is between groups, then there could be significant differences between the treatments. So, for example, if most of the variation is between groups, so between treatment 1, treatment 2, and treatment 3, you could say that there are significant differences, potentially, between these treatments as compared to variations within a specific treatment. And just for a little bit of terminology, as the only difference between the different groups we have is the drug treatment, this is what's called a one-way ANOVA. Okay? One way meaning there's only one difference between the different groups. If you instead looked at another factor, for example, gender, so you wanted to see how gender and drug treatment affected your ability to complete this puzzle, it would then be called a two-way ANOVA because 2 things are changing while you're analyzing the outcome of, in this case, solving a puzzle. So the first step in finding and calculating and doing an ANOVA is by asking the question of how much variation exists in the total data set. So our first step is to calculate what's called the grand mean. It's like the mean of the means. It's the mean of all the data sets, or all the numbers in the data set. So for a data set with A different treatments and N different measurements in each treatment, the grand mean is represented by this. It's basically, noting that I indicates rows and J indicates columns. It's just every data point divided by the total number of data points in the set. So for our example here, there are A different treatments. In this case, A is 3. So there are 3 different drug treatments. And N is 3, because there are 3 different measurements for each treatment. So our total big N in this case is 9. So our grand mean is literally all of these numbers summed up and divided by 9. So 3 plus 2 plus 1 plus 5 plus 3 plus 4 plus 5 plus 6 plus 7, all divided by 9. So our grand mean is 4. So again, we're trying to answer the question of how much variation exists in the total data set. Just to remind you, the first step is to calculate the grand mean, which we found to be 4. Next, we're going to find what's called the total sum of squares. And that basically asks the question of how much does each data point deviate from the grand mean. Okay? And as we're not concerned with the directionality or whether each data point is less than or greater than the grand mean, we square it, but it's basically each data point subtracted from the grand mean squared. Now this calculation has degrees of freedom associated with it, much like what we saw with the t-tests, okay? And the degrees of freedom in this instance are a times little n minus 1, or big N minus 1. Now, the question for that is why? So if you know the grand mean, you only need to know big N minus 1 of the data points to find the last one. So in this case, if you knew what the grand mean was, you would only need to know 8 out of the total 9 of the data points to find the 9th data point. Therefore, only 8 of the data points are independent from one another. One of those data points is actually dependent on the others. thus giving you degrees of freedom, in this case, of big N minus 1, or 9 minus 1, or 8. Okay? So when we actually do the sum of squares total, we basically subtract each data point by the grand mean of 4, square it, square each one, and sum them all up. And so when you do that, you get a sum of squares total of 30. And our degrees of freedom, much like we said, it's big N minus 1, or 9 minus 1, or 8. Okay? So step 1 finished. Step 2 is asking the question of how much of the total sum of squares of the SST is due to variation within each group. So how does each value in a treatment deviate from that treatment's mean? And that's what's called the sum of squares within groups, which is generally denoted as SSW. Sometimes you'll see it denoted as SSE, or for sum of squares error. And that is, in matrix notation, it's a value within a treatment subtracted by the treatment mean squared, and then you add all those up. The degrees of freedom in this instance for this calculation is A, which is the number of treatments, times the quantity of the number of values in each treatment minus 1. And that's because if you know the mean of a treatment, you only need to know little n minus 1 of the data points to find the last data point in the treatment. And you do this with A different treatments. Therefore, only A times n minus 1 data points are independent of one another. So if this is our data set in white, the blue row underneath is the mean of each treatment. So 2 is the mean of treatment 1, 4 is the mean of treatment 2, and 6 is the mean of treatment 3. So we go through and do the calculation. We do, for treatment 1, it's each value minus the treatment mean squared. So you can see this here. So it's these all are subtracted from 2 and squared, these all are subtracted from 4 and squared, and these all are subtracted from 6 and squared. And then you sum up all 9 of these calculations. You find that the sum of squares within the SSW, or the SSE as it's called, is 6. And the degrees of freedom associated with it is A, 3, times n minus 1, which is 2, or 3 times 2 is 6. So step 3 is asking the question of how much of the total sum of squares is due to variation between groups. So it asks the question of how much does each group mean deviate from the grand mean, and that's found through finding the sum of squares between groups, or the SSB. And in mathematical notation, it's shown through this summation. It has associated degrees of freedom of A minus 1. And to go through that, basically the grand mean is the mean of all the treatment means. So therefore you only need to know A minus 1 treatment means to figure out the last treatment mean. So that means that only A minus 1 means are independent of one another, which means your degrees of freedom are just A minus 1. So when we go through and do find the sum of squares between groups, this is the same data set before, and you can see that the row on the bottom in blue is just the mean of the treatments and of each treatment. So it's the mean of each treatment subtracted by the grand mean squared, and then you multiply that by n, however many observations there are in a treatment group. So we sum all of these together, and our SSB is equal to 24, and our degrees of freedom, which is just the number of treatments minus 1, is 2. So hopefully, or maybe something that you noticed in the properties of these ANOVA calculations was that the total sum of squares is always equal to the within sum of squares, the SSW, added to the SSB. And similarly, the total degrees of freedom is equal to the degrees of freedom between plus the degrees of freedom within. So you only need to know 2 of them to calculate the third. So that could save you some time, although to make sure you're correct, you should probably do all 3 and make sure that they all add up with these properties.